Welcome to episode 309 of CppCast, the first podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing today?
I'm all right, Rob. How are you doing?
Doing just fine. You got anything going on? You make any CppCon submissions? This is the last day.
This is the last day to make it.
It's the last days in the past, but the day we're recording is the last day.
Yes, the day this airs will be different. Yeah, I did make one submission.
Okay.
Hopefully it'll get accepted. That's all I know at the moment, I guess. I did also submit to teach a class at CppCon.
Oh, very cool.
So we'll see what happens there as well.
Yeah, I'm sure we'll find out news. They're usually pretty quick to do approvals for submissions, right?
Well, I don't know. The deadline is today, and then...
I'm not saying it'll be immediate, yeah.
No. People have to make travel arrangements and stuff if they're going to come.
Right. Okay, well, at the top of every episode, I like to read a piece of feedback. This week, we got a tweet from Antonio Natilla commenting on last week's episode saying, "This was so interesting to listen to. Thank you all for the episode." And yeah, it was great talking to Ivica last week about performance. It's been a while since we kind of just talked about the subject of performance. We kind of talk about it a lot without talking directly to it.
Right.
Yeah. Well, we'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us a review on iTunes or subscribe on YouTube. Joining us today is Hartmut Kaiser. Hartmut is a faculty member at the CS and EE departments at Louisiana State University and a senior research scientist at LSU's Center for Computation and Technology. He's probably best known through his involvement in open source software projects, such as being the author of several C++ libraries. He's contributed to Boost, which are in use by thousands of developers worldwide. His current focus is research on leading the Stellar group at CCT, working on the practical design and implementation of future execution models and programming methods. These things are tried and tested using the HPX, a C++ standard library for concurrency and parallelism. Hartmut's goal is to enable the creation of a new generation of scientific applications in powerful, though complex environments such as high performance and distributed computing, spatial information systems, and compiler technologies. Hartmut, welcome back to the show.
It's quite a mouthful, huh? Welcome back. How are you, Rob?
Doing
Hey,
great.
Jason. Nice to see you again.
Yeah, well, we may talk about this a little bit later, but the last time you were on the show was the first time I was co-hosting the show.
Which was exactly 300 episodes ago, actually.
Wow.
Yeah.
That's great. And congratulations to you guys for making that happen for the last 6 years. Right. That's quite an accomplishment on its own.
Pretty crazy.
Yeah.
Thank you. But also joining us today is Mikael Simberg. Mikael works at the Swiss National Computing Center, and as a scientific software developer, he has a degree in operations research and computer science. He works in industry doing embedded programming before joining CSCS in 2017. At CSCS, he works on improving HPX itself and helps users integrate it into their libraries and applications. Mikael, to the show.
Thanks for having me. Really nice to be on the show.
So it seems like we have 4 time zones covered today then.
Yeah, that's true.
Slightly unusual.
Yeah, but we got it working.
Yes.
This is still sort of the manageable time zones. And for me and Hartmut, this is quite a regular occurrence, but
Right.
it works.
Awesome.
I have to get early out of bed, and he has to stay longer awake. So just to make that happen.
Exactly.
Right.
I'm just kind of curious. Where is the Swiss National Computing Center, Supercomputing Center?
So the actual supercomputer, the headquarters are in southern Switzerland, on the border to Italy, in the canton of Ticino and Lugano. That's sort of the sunny part of Switzerland. I myself, I'm in Zurich. It's a bit further north, which is also sunny at the moment, but the weather tends to be better down south. Yeah, most people at CSCS are down in Lugano, and then we have a small 30 people or so up here in Zurich who are mainly software developers. Yeah.
I don't think I've spent any time in any of the Italian-speaking canton region down there.
There's only one.
There's only the one? Okay.
There's only one, yeah. But it's really beautiful down there.
I'm sure it
so
is.
If you ever get a chance to go down there, and whenever I get a chance to go there for work, it's usually a nice opportunity to just get to get the sun and get to see some colleagues.
Right.
Very cool.
And you get both the good side of Switzerland and the good side of Italy without having the disadvantages of either side, right?
Exactly.
So it's kind of unique.
Exactly.
All right. Well, we got a couple news articles to discuss. Feel free to comment on any of these, and we'll start talking more about HPX. Okay. All right. So this first one is an article from PBS Studio, and they've been sponsoring the podcast for a while. I really appreciate that. But this article is all about their mascot, and we always see the mascot in the blog posts that are coming from PBS Studio. And it was kind of fun to read this article about its genesis and evolution over the years that they've been blogging and using their unicorn mascot.
I still don't get why. Sorry, I still don't get why it's a unicorn. That's kind of still not quite clear.
I guess it doesn't matter. If you like it, then
Sure.
that's all that matters.
Yeah, I mean, they mentioned at the very top that they just used it originally as like a free piece of clip art that was out there, and people just loved it, and they kind of made it their own. And I guess I evolved it, and made it their own.
A unicorn vomiting rainbow. It conveyed what they wanted to convey.
Yep. I suppose I have to admit, I don't think I've ever used PBS Studio, and I was first wondering why you have a post about how the mascot developed and so on. Why does it belong on the show? But I don't know if I'm reading too much into it. But then when I actually read the post, I was like, well, there are details that matter in marketing as well, and just like writing software, these small things actually matter and can have an impact on how people see your product or project. So it's, as I said, maybe I'm reading too much into it, but I thought it was fun to think about it like that.
Well, they post a lot of blog articles about the kinds of bugs that their software finds. And those articles, besides the fact that they've been a sponsor, those articles tend to end up being articles that we discuss because often it's interesting. Like, what is it? I think one of the ones that stands out to me the most is they're like what is it? Shoot, it's like the last copy rule is I think what they've dubbed it, where if you copy and paste a block of code like 4 times, you always make a mistake on the last copy. And they showed the example of this, where you you correct that, you change the things you're supposed to the first 3 times, but on the 4th time or the last time, whatever the last time is, that's where you make your mistake. Anyhow, interesting stuff. So their PBS Studio can actually detect things like that. Copy paste bug detection is one of the things that they can do.
The first kind of thought I had when I was reading that article after you sent it is, damn, we really need an HPX logo.
Yeah, this can be your prompt to come up with something. You just can't use a rainbow barfing unicorn.
No.
All right.
We'll work on that, Hartmut. We'll work on that.
So the next thing we have is a post on Fluent CPP, and this is how to return several values from a function in C++. And when I was reading this, I thought we had used this as an article on CppCast a few weeks ago, but I don't think we did. I definitely was looking at it, though, a few weeks ago. It was dated July 9th. It's a good post, and talks about different ways to return multiple values from a function. Definitely recommends against using them, using like a pointer or reference as an input parameter and modifying it within the function body. It's definitely a bad practice. But talk about using a struct or using a pair or tuple and returning it that way.
Is it tuple or is it tuple?
I say tuple, but it's probably tuple.
I say tuple as well, but I never know what's right.
Yeah.
I very much prefer the name structs, and I think tuples or tuples, whatever you want to call them. It's nice for prototyping, but I don't think they really belong in production code in the end, because the only place is if you really have a sort of just a pack of arguments, parameters, which are really just first parameter, second parameter, and so on, and then tuple is perfect. But if you can get names to them, I always prefer doing that.
Yeah.
Tuples are very useful in generic programming, especially pre-C++20, when you have to capture a whole template parameter pack in a lambda and things like that. And they are very useful for prototyping, as Mikael said. If you do a bit of Python programming, then you kind of get used to that, right? You just return x, y, z, and then you unpack it on the other end, which is very convenient. So in that context, it's certainly very similar. But for production code, I rather prefer to have named structs. So that I completely agree with Mikael here.
Yeah. I think the one option that wasn't covered in the article that I'm aware of, which is admittedly questionable practice, would be to have used auto return type on the function and declare a local struct that has the named parameters that you want. If you say, well, it's only got a use in this one particular case, then you're kind of relying heavily on the person using an IDE so that they can, like dot member whatever and get the names of the things back out, because discovering that is harder, but it's just another tool.
Right.
Yeah.
Okay, and then the last post we have here is C++20 ranges avoiding dangling pointers. Jason, you want to tell us more about this one?
So this is interesting because it's one of the sorry, I lost the link myself. This is Andreas Fertig is working on a new book. So it's one of the chapters from his book. But this is just about avoiding the problem if you've got trying to iterate over some sort of container or range or something that is a temporary. And this is actually a problem with C++ ranged for loops as well. That is rarely hit by people. Have you all seen that issue where if you try to do a ranged for over a value that's returned from a function that's returned from a function, so you end up with a dangling object. Anyhow, one thing that stood out to me about this article was, so Andreas is going over what standard ranges did, but one of the things that stood out to me is that there's usually a mentality of that your compile error should be as soon as possible, but the technique taken here is to make the compile error as late as possible so you can give the most descriptive error. I've not seen that technique before, personally.
That's interesting.
Yeah,
Didn't realize that when reading the article. So, yeah, good.
Yeah, I hadn't thought about that either before, but I like the technique. And in a way, you're just tagging this type for later use. Okay, this can only be used in particular contexts because it gets a different type than what it would originally have had. And I think that applies in many other places as well. If you can put additional metadata in your types, you can actually avoid quite a lot of errors that way. It's always a trade-off. It's more work for you when you're defining your APIs, but it can pay off.
Right.
Okay. Well, Hartmut, as we mentioned, it's been 300 episodes since we first had you on, first talking about HPX. Do you want to start off by kind of telling our listeners all about what HPX is again and what has changed in the past 5 years?
Well, I'll try to be brief.
Sure, I'm sure there's a lot.
Well, HPX itself, we call it the standard library for concurrency and parallelism. In the end, at its core, it's a very efficient threading library. We have put a lot of effort into making it really, really efficient and reduce overheads as much as possible so that thread creation, scheduling, termination can be done in less than, I don't know, almost half a microsecond, which is very handy because you stop thinking about creating threads as overhead. You can manage very fine-grained parallelism, much more fine-grained than in conventional threading systems. And on top of that core, we have built several interesting features which make essentially HPX distinct from other what's nowadays called a asynchronous many-tasking runtime system. First of all, and that is what I would like to highlight, is the C++ conforming interface, conforming to the C++ standard. So what we have tried to do there is to say, okay, if somebody has a standards conforming program that uses standard facilities like std_thread or std_future or similar things, and flips the namespace from standard to HPX, it will work correctly. So the semantics of all the APIs are exactly following the standard. But you get the benefit that things run usually faster than what you had before. So a standards conforming interface of everything that the recent standards have specified, like barriers, ledges, threads, future, well, you name it, everything related to parallelism and concurrency. The second thing we have implemented on top of that efficient tasking system is a full implementation of the standard algorithms, the parallel algorithms that are in C++ 17. And we are currently extending that to be conforming to the range-based algorithms in C++ 20, which opens up very nice additional things. We can talk about that later if that's interesting. And the third thing that we have implemented on top of the tasking is we have extended, or we have tried to extend most of those facilities to the distributed case, so that you have a runtime system, or you can write code that is completely agnostic to whether things are happening on your local machine or on when you run it on a cluster, for instance, on a high-performance computing system, or whether things happen on the neighboring node. And all the networking, all the remote procedure invocation and everything is hidden behind the scenes, so that you essentially do a simple async with a function and you get a future back, and that function can run on a different node completely transparently. So in that mode, we treat, when you run an application on a high-performance system, you usually have that, well, you have the problem that you have several memory spaces, right? Each node has its own physical memory space. So you have that distinction, which reflects in these programming models which are used nowadays, that you have to specifically work differently when you access local data and when you access remote data, because it's different memory spaces, right? You can't directly address it. And there we have added a global address space, so that you can treat the whole application essentially running as if it was running on one giant machine, even if it runs on 1,000 nodes under the hood. And that is nice because you can move things around between nodes, which is a big problem in high-performance computing, because you want to achieve load balancing, and you want to move things around in a way that each node has the same amount of work. And doing that with conventional methods is very difficult. So that's kind of the three things we have in HPX. And I think that is what's distinguishing HPX from other similar implementations. Is that enough for now about what is HPX? Mikael, you want to add something?
I can expand on some of the things we sort of extend there, if you'd like now. Or, I mean, I could maybe specify when Hartmut says that we, essentially run a thread pool underneath the hood, and we have these lightweight threads specifically for people maybe coming from other languages or other frameworks. They're stackful threads in the end, so just like stud threads, you can yield them and suspend them and so on. And this is why we can actually have things like mutexes inside these threads. On the other hand, it also means that while they're a lot cheaper than standard threads, they're still not for free. So there is some overhead there as well, which is something you still need to keep in mind. HPX just shifts the minimum grain size. So we usually talk about the grain size when we're talking about sort of the task size or the size of the amount of work that you want to actually submit as a task. That's usually the grain size. And with standard threads, you need to have quite a lot of work for it to make sense to actually spawn a new thread. With HPX, that shifts much further down. So you can have much smaller tasks, but there's still a limit. The other thing is, okay, our futures, again, Hartmut sort of implied it, but standard futures just are on their own. You can standard async, you get a future, but you can't really do anything with it except get the value at some point. With our futures, you can chain them. So the .then, there are other futures libraries that allow you to do that as well. But I think that's one of the key features, actually, that you can chain these tasks and build up complicated graphs of tasks using these primitives. And then I suppose the third thing I wanted to add is that for the parallel algorithms, again, the ones in the standard library take various execution policies, but they're all blocking calls. And this is one of the extensions that, so this was there before I even joined or started working on HPX, is we have a sort of task policy for the parallel algorithms, which allow you to run things either sequentially or in parallel, but then on top of that, you get a future to the result.
Oh, interesting.
That means that you can actually, not just have your individual tasks that run then, on one thread, but you can have a full parallel region as part of your task graph, which is pretty cool.
Well, the main benefit of that is, if I may add, the problem of and one of the questions you wanted to ask today, am I happy with parallel algorithms in standard, right? Well, yeah, in some sense, I'm very happy about them. On the other hand, they are very limiting because they still give you fork join parallelism, right? You fork a couple of threads, right, and then you join them in the end. And what many people don't see when they use that in OpenMP or even the parallel algorithms is that join operation is what costs your DLA, especially when you have a large number of cores or threads you want to join at that point. So that join operation can add significant overhead to your overall execution. By launching a parallel algorithm on the side asynchronously, you still have that join operation in the end, but you can part of the cores free up early, right? And part of the cores have to do the join operation in the end. By moving them on a side and executing it asynchronously, you can do other work when the cores free up. So you can kind of mitigate that join operation very nicely in the end by doing other possibly unrelated work on your main execution flow, if you want. So that gives you performance benefits, even if you would think, hey, I'm adding more overhead because I'm getting the future back now. No, you're saving on the join operation, which is one of the main culprits actually of the existing execution models we have. People just slap an OpenMP pragma in front of their loop and say, yeah, great, I parallelized that thing. No, bummer, will not work. So
yeah.
Okay,
oh, yeah, sorry. So I just wanted to say, I guess specifically, it's Amdahl's law that kicks in where, if you have your fork join, it's the serial regions that kill you in the end. You try to run it on, 128 core, dual epic system or something like this. And it just won't scale the way you want if you're doing fork join.
Yeah, that's two questions I had is, what do you call when Hartmut said if you have a lot of cores? And I'm like, what is a lot of cores to them? What is a lot of cores to you?
Well, the biggest run we've ever done with HPX was using 650,000 cores.
Okay, that's definitely a lot.
on I don't know, 5,000 nodes, something like that.
Okay.
So each node has up to, I don't know, 256 cores, physical cores on their high performance computing systems. So that there, if you run it on your laptop with 4 cores, then the join operation probably will not be noticeable or
Right.
not that significant. But if you run it on a large system, then these join operations really Oh, Amdahl hits you over the head here, right? So you add sequential execution, and you force your execution into some sequential piece, and that is exactly what kills your scalability.
So then also, I was thinking about, we were talking about how some of the cores will get freed up earlier in a parallel operation. So I want to make sure I understand. You're suggesting if you know that you have like 3 algorithms that could run in parallel, then with your version of these algorithms, you could say, okay, future for those 3, and then you ultimately get, as much as you can, complete utilization of your cores. As soon as some processes start to free up on the first algorithm, the second algorithm will just automatically start using them. Does that sound
correct?
Right? Okay.
Yes. If you have 3 algorithms in a row, then when you do it synchronously, you get these 3 join operations.
Right.
And that is a big pitfall. And that's, by the way, where ranges come in. Because, and that's what we have added to the, I said we are currently implementing the C++20 range-based algorithms. And what we have done, we have added parallel versions for those algorithms as well, even if the standard doesn't specify them. So essentially, you can pass an execution policy to the range-based algorithms as well and parallelize the range-based ones. And that is very interesting and non-obvious, because what libraries like the standard range library or range v3 do for you is silent loop fusion. If you have 3 algorithms and you join them with a pipe in the range-based world, you pipe them, right? That essentially means, and the main reason you want to do that, or the goal of allowing that, is to avoid the temporary arrays in between the algorithms. And that means that these 3 algorithms are executed not one by one, but element by element. So the first element will be kind of dragged through the 3 algorithms, and the second element will be dragged through the 3 algorithms, and so on, because it's the only way for you to avoid the temporaries in between. And that means you fuse the 3 loops into one bigger loop, where one loop executes the 3 operations for each element consecutively. And that means if you parallelize that one, you suddenly gain a lot of potential, because you parallelize the fused loop instead of parallelizing these 3 separate loops.
Okay.
And you don't have to do anything. You just use the range-based parallel algorithms and pass a sequence of piped algorithms, piped range-based algorithms to it, and you get loop fusion, which is another big gain. That's what you normally would do by hand, right?
Wow.
If you have three algorithms in a row, you would try to fuse the 3 loops yourself by hand. By combining parallel range-based algorithms with libraries like range v3, you get that for free.
So for your parallel range-based algorithms, do they actually have like different names, like par underscore for each or something? Like, what does this look like?
No, they are just in a different namespace.
Oh, different namespace. Okay.
They are in the ranges namespace and take the normal execution policy, the par execution policy, and then the interesting thing is that they don't do much. They essentially just rip the range apart into begin and end and pass that to the underlying implementation. That's the whole trick there. But it opens up these loop fusion, automatic loop fusion effects, which are very beneficial.
So do you use like a expression template kind of technique or something to fuse the loops? What is that actually? I'm curious how it's actually implemented.
Range v3 is doing that. We don't do anything.
Oh, it does it on. Okay, then I didn't realize that.
And the standard library has these piping operators as well, I believe. Mikael,
yes.
Do you know that? So it will do the same thing. It has to do it to avoid the temporaries in between the algorithms. Otherwise, it wouldn't work, right?
Okay.
Yep.
The only way to implement that without creating temporary arrays or temporary containers in between the steps is to do it element by element wise. There's no other way of doing that. So they have to fuse the loops.
Okay, I missed that detail. That's pretty cool. And you brought up one other question in my mind as you were describing all of this. And actually, coincidentally, I wasn't even thinking about this. I just released an episode on C++ Weekly this morning that is about the C++ 17 parallel algorithms. But it's a super high level episode. It just shows, look, if you have the right workflow, right data, you can, magically get faster algorithm. But one of the sore points for me is that libc++ still doesn't have parallel algorithm support. Can I take HPX and just drop it into my code and now it'll work on Clang on Mac OS and boom, I magically have parallel algorithms available to me? I mean, like, is it portable across all the platforms?
Wouldn't that be cool? but I think Mikael has something to
Pretty
say.
much. Yeah,
pretty much.
So that's the goal. So Clang and GCC are well supported. Hartmut uses Windows, so we support Windows as well, or Visual Studio. Mac OS is a bit difficult. We're not too many people working on this, so we sometimes have breakages there. And really, you need to have someone who is actually dedicated to fixing these things to be able to support it. So we try to do it as well as we can. We often have, patches or PRs coming in from people who, fix compilation on their platform, sometimes on BSDs, things like this. We can't, unfortunately, support it fully ourselves, but wherever we can, we try to be as portable as possible.
Okay.
Well, I think there was a part to the question which I would like to add to. Can I just use the HPX parallel algorithms and drop them into the existing code I have? And that is a bit more problematic, at least at the moment, because currently the HPX algorithms use the HPX threading system underneath, which is not fully compatible with other threading you might do yourself. So that
all
is
in or not then?
Yeah, at the moment, yes. But and that's what I was hoping Mikael would jump in, because what the C++23 is aiming at is, and you might have heard about that, is the executor discussion, which is nowadays not an executor discussion anymore. They call it schedulers nowadays, but
I didn't
whatever.
know that.
But the idea here is to create infrastructure that allows it on the standard library level to combine different threading implementations into one. And this is based on senders and receivers, so a very low-level abstraction mechanism of building asynchronous execution chains by having senders which give you some value and receivers that receive those values, and that is standardized. And the effect here is that you will be able to move execution between execution environments like GPUs or threading systems like HPX or standard threading. And once all of this is in place, and that's our goal to get that implemented, we will be able to use the HPX standard library standard algorithm implementations directly in the context of your normal C++ program. Because then these algorithms will be agnostic to the execution environment they are running on. And we hope to achieve that at some point, yes.
Okay, so let's just say I have two questions now. If in my code I am currently only using the C++ 17 standard parallel algorithms, and I say, okay, I'm going to switch fully to the HPX model, based on your lighter weight threads, would I expect to see, without changing anything else, a performance difference?
Yes.
Okay. That's a very straightforward answer.
I would expect that, yes.
Okay, and then the other question is, no, I don't think the other question. I don't think I have another question. But the point is, I have to go all in on your threading model at the moment. If I want to do that. Okay.
Yes.
At the moment, yes. This was already mentioned with the benefit that ideally you just need to change STD to HPX. So the transition would be fairly straightforward.
Well, I'm just thinking like on another project that needs to support like all three major operating systems. If Mac OS isn't very well supported, but we can get the performance boost that we want on Linux and Windows, then it sounds like I could just use namespace HPX into a local namespace somewhere, swap it at compile time, assuming I stick to the standard things and don't use your more advanced features, then that sounds like a perfectly reasonable option for some people.
But by the way, if I may have a plug-in here. So if somebody of the audience is interested in helping us with supporting macOS, please get in contact. We are always we're a very open community, and we would like to have more people helping with developing it.
Yep.
So I think we've mentioned a couple of the features that were released in the newest version of HPX, which is 1.7.0, I believe, right? So that included the ranges support. What else is new in this new version, 1.7.0?
Suppose one of the things, I mean, Hartmut, you can tell more about this, but GCC or lib standard C++ has support for the SIMD types now, experimental, but still. And this is something we've been doing for a while as Google Summer of Code. We currently have a student working on essentially implementing policies based on GCC's SIMD implementation, which is quite cool. And as far as I've understood, the performance seems to be quite good, and it's been quite a smooth transition. We used to have, or we still have, support for VC, which is another vectorization library. But eventually that will just get replaced by the standard support for SIMD. So that's one big thing. I don't know, Hartmut, do you want to add anything about that?
Well, I'm going to go ahead and interject right here that you should probably give our listeners an overview of what SIMD means and what that actually looks like to use it.
Well, SIMD means, SIMD stands for Single Instruction Multiple Data, and is a means, or is the execution model which is used when you vectorize, or when the compiler is vectorizing code. Essentially, let's assume you have a for loop over floats, and you calculate something for each of the floats in your input array. Then compilers might be able to vectorize that by, instead of doing one operation at a time, just put it into the vector registers and do 4 or 8 operations in one cycle. So, and these SIMD types that are now in the experimental, STIT experimental namespace in GCC, and it's libc++, right? I think.
Lib standard C++. I think that's a new one. Yeah.
In the GNU library. Essentially introduce types that encapsulate vector registers in the CPU.
Okay.
And overload all the operators on those types so that you can use those types as if it was a single float.
So I can say very explicitly, I am using 8 floats or whatever in this register. Now do these things on them. Okay.
And that maps onto compiler intrinsics. So it's generates fairly efficient assembly code underneath, which is optimally close to what you do by hand when you add vectorization yourself. So it's a very convenient way and a C++ way to do vectorization, explicit vectorization, and not rely on the compiler, but do it yourself. Essentially, have full control over what's happening. What these algorithms, the relation to the algorithms, what Mikael mentioned, is that we have added special execution policies like par or sec, which are called SIMD and SIMD par, that instead of calling the lambda, which represents your loop function, your iteration, with one element, it calls it with a SIMD type that holds 8 elements or 4 elements. So your lambda now can operate on vector types automatically. So you essentially you write the code as if it was normal non-vectorized code, but the loop function will be called with a vector type. So you have a lambda with auto as a parameter type, and the compiler will deduce that correctly. And since all operations are overloaded for the SIMD data types, it's fairly straightforward to make work properly.
Okay.
So by just changing the execution policy, you can, for arithmetic-based kernels, you can easily achieve factorization and have full control over it, even in the standard parallel algorithm world.
So it's a new execution policy,
Yes.
parallelization policy that you added.
Yeah. Well, vectorization. It's simply
Okay.
for sequential, only sequential vectorization, and simply par, which is doing both vectorization and parallelization. And the nice thing here is for compute-bound kernels, we see speed up of factor of 250 on 8 cores. Well, no, 16 cores. 16 cores. I don't want to lie. On 8 wide vector registers, which is just amazing, right? You if you compare that to sequential execution, just getting a speed up of 250 by changing the execution policy is quite a feat, I think.
So you're saying going from a serial to parallel with vectorization 250 times. Okay.
Yeah. On compute-bound arithmetic kernels.
And so this does kind of you must be operating over floating point types. Is that correct?
Well, anything the vector units support.
Okay.
So it could be integers, could be floating points. So some integral data type supported by your CPU.
So now does the system then like basically falls apart? If it was even just a struct of 2 ints, then there's no way for you to automatically decompose that and do a thing on it.
There are tricks you can do that by using zip iterators and adding support for zip iterators, that you take it apart and repackage it as a zip of 2 vector registers, things like that. Right. But we haven't done that explicitly at this point.
Yeah, no, I'm just super curious, so I'm just kind of sussing out where the corners here on this, because that I think I can visualize what you're doing, and it sounds really cool. So
that work is driven by Matthias Kretz. He is very active in the standardization community, and he has implemented the SIMD types for GCC, I believe. So he's doing all that work there and specifying things. And the SIMD par and the SIMD execution policy are his idea as well. So we just took again what the standard is trying to do and where we are trying to go with the standard, and create some experimental implementations to see how much effect do we get.
So if I do the SIMD thing and get this awesome speed up, but then I go and recompile on Windows, it'll still compile. It just won't be able to it won't be able to do the SIMD thing because you don't have the SIMD intrinsic, or you do have the intrinsics, but you don't have the SIMD types that GCC offers on Visual Studio.
Correct. But there you can use VC as that other library. That is not really supported anymore, but at least for the time being, you can use other libraries there.
Okay.
That do very similar things.
Yeah. And I guess
you just mentioned standardization again. I was just curious, how involved are HPX team members with the future of the standards? Obviously we talked a little bit about executors, which is really no longer executors. So how involved is HPX in the direction of this?
It's a mix. I guess a long history. Hartmut has been part of the executors discussions years ago. I guess at some point, it just drags on and on. People come and go. I've recently just, started joining some meetings just to listen in, and, eventually we hope we can actually contribute something in the form of feedback, because now we actually have an implementation of at least parts of the new proposals. So that was sort of the third big topic in our last release is support for senders and receivers. And I guess, yeah, it's an interesting topic because, we have standard futures, which are very much tied to standard threads, quite heavyweight. And we have our own implementation of HPX futures. And we will keep those around. But these always involve heap allocation for shared states and things like this. And senders and receivers are really sort of a generalization of futures and promises, in a sense where you can, in the best case, avoid lots of allocations. They're a very generic framework for chaining various asynchronous operations, not necessarily even asynchronous. You can also write synchronous code, but if that's all you want to do, then you might just write it sequentially. But it's quite a neat framework, and I actually hope that it's gonna finally take off and maybe even make it into C++23, because so from our experience it looks quite nice and has worked quite well. There are certain things when you start dealing with network communication, for example, MPI is one of the big things we deal with in the HPC world. And then, of course, accelerators with CUDA, AMD's HIP, and there's Intel's SYCL, for example. These are all quite important because in all these cases, you're dealing with asynchronicity. You launch something on a GPU, and trying to combine these is one thing, which we have been able to do with Futures, but there are certain overheads when you're dealing with just plain Futures. There are certain optimizations that you can't at least do cleanly with just plain Futures, and senders and receivers allow you to do that sort of officially according to the the sender concepts, the receiver concepts, and it all gets optimized quite nicely.
Okay.
Yeah, so we've been, I've been involved with standardization for 10 years now, I think, on and off. So I didn't go to all the meetings, but I attended quite a couple of meetings, and at least we haven't been really able to directly influence things in the standardization committee, because we're kind of on the fringes, right? University, you're dealing with big companies there when you're doing standardization. But I think we have at least reported back on the results we had, and we have influenced things or confirmed things and helped moving things forward, even if no direct features we have used have made it into the standard yet. But the fact that we have confirmed, for instance, the concurrency TS1, which was specifying the futures exactly in the same way as we have them now in HPX. So with .then and these methods of combining futures were all specified there. So we have taken all the things from there. And our experience has at least helped deciding whether to go ahead with it or not. And in the end, we decided not to go ahead with it because of the things Mikael mentioned, right? There's quite some overhead associated with it, and we can do better than that. And that's one of the reasons why the concurrency TS1, the technical specification 1, didn't go into the standard in 2017, I believe.
Yeah, I was going to say 17. Was
it was dropped on the floor because of that. So we had some impact, even if not directly visible. And I think that's the best we can do at this point.
I think I just wanted to add that I think that's one of the key things that, implementation experience, I think that's quite important for standardizing things. There are a few other implementations currently of senders and receivers, but I think with HPX, we have actually quite a, large and diverse code base where we can test these ideas out, especially, like I said, with accelerators and in actual applications. Not saying that other people don't have applications, but we have at least one interesting use case in HPX applications. The other thing I wanted to mention is that even if we don't directly influence the standards, I hope at least that we're making people aware of the ideas that are being proposed and hopefully actually going into the standard library, like you're on the show right now, but also. For example, at CSCS, they've been quite involved, and users and scientists writing scientific applications, get directly exposed to these ideas, and slowly they will hopefully trickle into their applications as well. If there were fewer people doing that, maybe in 2030 we might see people actually adopting these things. If we tried to push, it might happen a bit earlier at least.
These conversations just make me feel like I'm getting old. I'm like, in 2030, am I going to care still? That's like 9 years from now. I'm going to be thinking about retirement.
Yep.
If you don't mind if I do just a little bit of historical digging, because Hartmut, if I recall correctly, you were involved. Well, you did mention explicitly that you were involved in Boost, have been involved in Boost for a long time, but you were involved in like Boost Futures specification or implementation a long time ago, were you?
Well, I proposed a library in 2004 implementing something that it was very similar to standard futures. Yes. Okay. At that point, nobody picked up on it because they said, hey, why do we need that crap? So it didn't go anywhere. But that was the first time I kind of dug into futures. And I still think it's a very neat feature which allows to do a lot of things in a very convenient way. Mostly because it gets away from the notion of threads. Because I believe people shouldn't use threads directly. No raw threads, just to add one more paradigm to Sean Parent's list of things, right?
No raw new, no raw loops, no raw pointers, no raw threads.
Right.
Also, no raw synchronization primitives. That goes along with raw threads.
Absolutely.
Yeah. Well, you still need some sometimes, right?
Yeah, but
even with futures, you have to do things. But if you work with value semantics and try to make your tasks self-sufficient with no global side effects, then you don't need synchronization at all. So that works very well.
Yeah, well, for the last 10 years or so, if I have to write parallel code, I aim for futures, no explicit synchronization, and then send C++11, maybe pass around an atomic occasionally if I have to. It's like a stop token. But now we have stop tokens, so I don't have to do that anymore.
Yeah.
Mikael, I was wondering, in your bio, you mentioned that in addition to working on improving HPX itself, you help users integrate it into their libraries and applications. I'm just curious what that looks like. Obviously, we've talked about how you can just change the namespace from STD to HPX and get a lot of performance improvements. What else are you doing with those users?
Yeah. So one of the main drivers of us developing HPX at CSCS is distributed linear algebra. This is a sort of big topic for many of the scientific applications, where linear algebra comes up surprisingly in scientific applications, and they need to do it efficiently. And many of the existing libraries, they do fork join, they do a lot of sort of explicit synchronization, sort of global barriers using MPI, which is, if you have a distributed application, you synchronize between each step. And just like, on a node, you end up with sequential portions of the code that doesn't scale that well. So one of the developments we have is a library called DLA Future, which is the future of distributed linear algebra, but also based on HPX futures. And this is, really a good test case and a good, I think, application also for HPX. It plays to the strengths of HPX. So what you're essentially doing is you want to do linear algebra on your matrices, and you split these matrices up into blocks, and they live on different compute nodes, and then you need to do some operations on these. And by dividing your work up like this, you end up with discrete tasks. You want to do a matrix multiplication on one node, then you wait for the result from some other node, and it kind of plays very naturally into this task-based programming flow. And then, like we already mentioned with parallel algorithms, if you have multiple parallel algorithms that are independent, again, this sort of naturally just load balances. You get another algorithm filling in the gaps on one worker thread once it runs out of work. So what we're developing at CSCS, this is not my project. It was led by a guy called Raffaele Solca, and essentially we're helping them build this library. At the moment, it's a sort of generalized eigenvalue solver specifically. I know little about the actual science behind it, and the goal is is essentially to beat the existing state-of-the-art implementations, which I think we're actually doing at the moment already. There's still some development work to be done there, but at the moment it's looking actually very nice. And then the next steps would be actually integrating this into applications that do the real science. This is just the library that does the linear algebra, and it sort of goes stepwise closer and closer to users.
I'm thinking, Rob, through the course of this conversation here, that our guest a few weeks ago, Andrei Chertik, working on his Fortran implementation, should use HPX, because the nature of Fortran means you can prove some of these things right out the gate. You can say, oh, well, I could apply a parallel algorithm here. It's only floats, use HPX, and just automatically get super fast C++ output from his Fortran C++ compiler. You all should collaborate on this somehow.
In the end, that's an application HPX was made for. It's a runtime system. It's to be used by others to speed up their library, their application, their whatever they want to do. So it's never meant to be used as a thing on its own. It's always really just the environment that sits on top of the operating system and gives you more efficient facilities, very much along the lines what the operating system gives you, but focused on a single application. If the operating system is kind of the mother of everybody and tries to make it good for all applications that run on the same node at the same time, a runtime system is very egoistic. It just cares about the application it's related to and linked to. And it doesn't care what the others do. It just grabs all the resources it can get and it utilizes those. And so if you can integrate that as something in a compiler like you mentioned, or into a library, you don't even have to expose that to the user.
Yeah.
You use it really just as a facility that allows you to speed up the code you're generating. So that's one of the perfect applications for this. Yeah, I would love to see that happening.
Sounds pretty cool.
So maybe to close this all out, is there anything you can tell us about, Hartmut or Mikael, about the upcoming features of HPX that you want to preview?
No. So we still definitely have some work to do with senders and receivers. That's at least a high priority on our side at CSCS. And sort of integrating that into applications, getting more field experience with how that works, and seeing what kind of optimizations we can do with those. That's number one for us, I guess.
Mikael and his team are mostly worried about using HPX for local parallelism and leave the distributed part to things like MPI or other systems. We're here at LSU are very interested in the distributed part of HPX as well. And we use it for several applications, very large scale applications. And I really hope that we can move forward on and perhaps extend the sender receiver concept into the distributed world, which sounds very promising. So senders receivers is really a big topic I see for the future. But standards conformance in the general case is very important to us because that lessens the learning curve for people, right? When they come with their own C++ code and they know C++, it's not a problem for them to switch to HPX because in the end, all they have to do in the first place is change the namespace and be done with it.
Yeah.
And from our experience as well, when people come on to the project, they are not struggling with HPX itself. They mostly struggle with C++ and with modern C++, which we really try to use for implementing things. So using the HPX is very simple and straightforward if you know C++ well. If you believe that you know C++ and you know how it is, right? Everybody thinks they know C++ on a scale from 1 to 10 at about 5, right? No matter whom you ask. Whether it's a newbie who has attended one lecture in university, they believe, 5, yeah, I know what that is about. Or if you ask Bjarne, right? Bjarne says, I'm at 7 or something like this.
Yeah, and you get really nervous if someone says 9 or 10 because you're like,
That wasn't.
Yeah.
I know only 2 people I would believe what they said. Yes. Okay. So just to round that up, if you're interested in HPX and want to try it, feel free to get in contact. We are more than happy to support you. The team around HPX is a very large team. We are kind of have representing or people contributing all over the world, from South America, North America, Europe. I don't think we have anybody in Africa. I think we had somebody in Egypt at some point. Russia, China, Japan. So please join the team. It's a very nice, large open source team with a very open atmosphere, and one of the few channels, IRC channels, that are not hostile. So please, everybody's welcome.
Yes.
I guess on that note, where should our listeners go if they do want to either join the team or just maybe looking for help in getting started, getting your own stuff to run using HPX?
So I guess, we're on IRC at Matrix, libera.chat. There's the Stellar channel, but the easiest way to find that is through hpx.stellargroup.org. That'll be in the show notes. And there are links to different ways you can contact us. We also have a mailing list, both for users and developers. And you can follow us on GitHub for releases and just checking what's going on with pull requests and so on. It's all public and open. We try to hide as little as possible, warts and all. I think the website is the best entry point to actually find us.
Perhaps I want to add that the license HPX has been published is the Boost software license. So it's very liberal. You don't even have to tell us when you use it. So very open, no strings attached.
Oh, is it supported by any of the C++ package managers? Can I use VC package or Conan or something?
Yes. Well, not Conan. We have VC package.
VC package, okay.
We have Spec.
Spec, yes.
But
of course.
Spec is more HPC related.
Yeah.
We would love to have somebody working on a Conan package. People are asking for it, but we didn't have the bandwidth to look into that.
Okay.
Yeah.
All right. Well, Mikael and Hartmut, thank you so much for coming on the show today.
Oh, thanks for having us.
Yep, thanks for having us.
Thank you.
Yes, yes, you can do that, but you certainly can have that output. As you are running your cache to test, you can basically take that output and then pass it to the Tuka server. So in this case, you are integrating the Tuka client library with your unit test, executable. So that's possible. And I think I like that approach more than having your output stored in a file and then later have a separate kind of process for submitting that output.
Right. And can Tuka tell you that, some numbers trending down or trending up or staying flat? Okay.
Yes. So I guess at this point, the analytics that we provide for the behavioral differences is slightly more mature and more helpful than for the performance. However, Tuka can show in its UI the trends of differences for different functions over different versions of the code. And I have found it very helpful because usually, you want to look at a chart and see that over time, your tiny little code changes kind of amount to a performance hiccup or a slowdown in a piece of workflow. So all it does right now, the interface is just giving you a chart, showing you how the performance changes over different versions.
For many things, that's good enough. Yeah.
Yes, I think that might be enough for people to find value, but I have much higher ambitions in terms of how to make it more helpful for users. In this case, I really think that tracking performance is slightly more tricky than behavior because it usually has some noise.
Right.
It is not guaranteed to stay exactly the same. So you want to have a way of looking at the performance changes as a human being looks at it, right? We look at a chart, we say, oh, well, this dropped 1% or 2% for this particular version, but we don't care as long as this is not consistent over a few versions.
Right.
Should we talk more about like the actual Tuka website interface and what that process is like? I did watch one of the videos you put up that was linked to that article 2 weeks ago.
Awesome. Yes. So again, I think the Tuka server helps you not just store your results, but also compares them against different versions. Now, the comparison certainly has some output in the differences. So the server attempts to visualize those differences. And the visualization of those differences is something you can look at for each given version. As your test is being executed, you can go have a look. But then after all the test cases are executed, the server is going to send a notification to members of your team and say, hey, this particular version that you just ran has these differences. So that report that it generates is more high level because it's meant to be consumed by everyone to give them an insight into how this particular version has behaved. So that you can look at that email or Slack notification and say, well, this is not what we expected, so let's go take a look. But in some cases, you may make intentional changes to the software, in which case you would use the platform again. You go there, you click a button and say, "This from now on, this is the version that I trust, that my software should behave from now on." So that is also kind of automated, the way that all these versions are basically tracked. You can add comments to kind of communicate with your team members, and then have audit logs for how your software is evolving over time.
Yeah, do I need to inform the Tuka server that I'm going to add some new variable or value, or can I just do that ad hoc? Okay.
You can do that ad hoc, yeah. In fact, you can do that with test cases as well. You can add as many test cases as you want at any one time. the advantage of having this remote test server is that it is aware of the test cases that are part of your baseline version, right? So the advantage for that is you can then not have your test cases listed as you're running the test. So a normal Tuka test code doesn't specify its test cases, because when you have access to the library can query the list of test cases from the server. And therefore, you don't have expected values and you don't have the list of test cases. All you have in that regression test code is how you run your workflow under test, and then what data you want to capture.
Okay. I don't think we've mentioned yet what platforms, compilers are supported.
Yes. So the C++ client library for Tuka has support for all platforms. So all known commonly used platforms, right?
Windows,
Linux, and
so I can work on my Commodore 64 code that I've been. No,
I am regretting to say having said that, but in general, I think because the end users might be using code bases that are somewhat dated, I wanted to support a wide range of compiler versions, a wide range of standards. So starting C++11, it kind of covers the relatively recent versions of the C++ standard. And then the compilers, I think GCC 8 and Clang 8 are both supported, as well as MSVC. I think for 2013 is supported, wow. Which is giving me a lot of headache, to be honest.
Yeah,
so you might drop it.
No.
Yes, you might drop it going forward.
Yeah,
that's right. Yeah.
I think 2015 would even cover most of the current console dev kits, actually.
That's right. However, because this started as a side project and then kind of obtained as an internal tool at my former employer, I had to make it possible for us to use it with the most outdated codes that we had, which happened to be using MSVC 13. So.
Okay, so I feel like I should ask this, or I'm very curious anyhow. You mentioned in your bio that you recently left your former employer to pursue this, and then you've also just publicly said that you began development of this project at your former employer. So you left with their blessing, I assume, to...
Yes. So for our listeners, so at least in the US, I think the norm is that when you start working somewhere, your future IP, developed IP, would belong to the company that you are working for.
Right.
And that seems a little weird for others, but here we all understand that. Now, the problem was, because this was started when I was working at my employer, so I basically had to work on it only at nights and weekends. But then, because I was so obsessed with it and everybody knew that I'm working on it for so long, they all had my, kind of their blessing. So I got the IP rights, and that's only when I was able to start speaking with people and showing the product to them outside the company.
Oh, and the way you had described it, I thought that you had actually started development on this on the company's dollar, which they would own it, I think, in pretty much any country if that had been the case.
That's right. Yes. Yes. But this was a side project. And for me, it was very important to kind of separate the work that I am doing for this project with all the other work that I do for the company,
right,
tasks.
Okay.
So that's cool.
Yeah.
You said you've been working on this, I think, for 2 or 3 months, kind of on your own.
Full time. That's right.
How well has that been going? Like, are you getting funding? Do you have users?
No, I don't have funding yet, and I'm not seeking funding right now. I'm seeking my first 10 customers, 10 paying customers, I should say.
Mm-hmm.
I have since leaving Vital, I have now about 10 active individual users that are using the product on a weekly basis. Now, there are also a couple engineering teams that are evaluating the product for larger scale use in their organizations. Now, I still don't have any paying customer, and I'm actively working on finding my first 10. I want to say right now that my primary objective is to get as much feedback as I can from actual people who have this problem, the problem that we had at my company. So the conversations I've had with software engineers over the past 3-4 months has been extremely interesting. Just to find that we all are suffering from the same issues is kind of giving me goosebumps. But in general, it's also very motivating in terms of the possibilities of improving what can be improved in terms of how we maintain software at large scale.
Right. Well, so if listeners are interested in trying out the project and becoming a user, paying or otherwise, what kind of options are there?
So right now, the platform, so I should say that the remote Tuka server can be deployed on-premise as well as a cloud-hosted version. So the cloud-hosted version is deployed at tuka.io. Listeners and anyone who is interested can actually go create an account for free. They can use the client libraries for C++ and Python to submit test results. So everything is free right now. But once they want to use it for teams of up to, say, more than 5 members, then right now there is a pricing plan, but it's still I don't want it to be a blocker. I want to kind of just have users that are using the product and not worry about paying. So in general, everything right now is as free as it can be. And I'm going to keep the free plan for the tuka.io platform, forever, permanent. So there's always a way of, working and getting value out of this product without paying anything.
Okay.
Very cool.
So like I mentioned before, the project I'm working on already has a regression solution that does work. So I don't know if we would be interested for this particular, for that problem with your solution. But I am really needing to start tracking more statistics, like binary size, bloaty output, ABI diffs, that kind of thing. Can I use the Python interface to push those things in a meaningful way to?
Yes.
Okay.
So I think it was 2 weeks ago when you mentioned that on a podcast. And it's interesting that it was the first time that I was thinking of this, being a possible use case. And therefore, I was interested enough to try it with the new client library for Python. So I'm calling the ABI diff and then getting the output and submitting it to the platform. It's very simple. So by the time that this podcast is released, I'm hopeful that I can have a GitHub repository that is public that shows how to do this, so that anyone who is interested can try.
Awesome.
Very cool. Okay, well, where should listeners go if they want to go and try out Tuka, Pejman?
I would recommend that they start with tuka.io. There are links there, especially in the documentation, to GitHub repository for the C++ client library if they want to start integrating that and then getting started. And there are so many different getting started guides in terms of, just if they are curious to get more information about how the platform works.
Okay. Anything else you wanted to tell listeners about before we let you go, Pejman?
Well, I just wanted to mention that this project started with a C++ client library, so it's near and dear to my heart in a way. And I feel like the best that I can get out of the C++ community is their advice and feedback. So I'd like for your listeners to see if, check out the product and then see if they can find it useful or not, and then share their thoughts with me as I'm starting this journey. Another thing I wanted to mention is for the past 3-4 years that I've been listening to this podcast, I've been thinking that I would come, if I would ever join you, I would plug the work that you're doing at my former employer now, which is certainly interesting, technically very challenging, and for a C++ engineer, it's the best type of work that I've ever experienced. So I'm sure that we are still hiring. And if you're interested, looking for a fun challenge, check out Vital Images.
Vital
I don't
Images.
think we've ever talked about medical imaging on the show before, but I'm sure there's a lot of C++.
I turned down a job that was related to medical imaging because it made me too nervous. What if I got something wrong? I didn't want to kill someone, basically.
Yes, but on the flip side, writing good code might actually save someone's life.
Yes, that's what my wife tells me, but yeah.
Okay, thank you so much.
Thank you again. Yeah.
Awesome. Thanks for coming on.